In the direction of the constellation Boötes, 700 million light-years away, lies a region of space 330 million light-years across. If the Milky Way sat at its center, astronomers would not have known other galaxies existed until the 1980s. Astronomers call this vast expanse the Boötes Void, a colossal region containing almost no visible matter. Based on the average density of the observable universe, a volume of this magnitude should contain roughly 10,000 galaxies. Instead, survey telescopes found almost nothing. Popular retellings often describe this void as a total vacuum or an unnatural barrier built by advanced alien civilizations. The physical reality is different, but no less dramatic. It stands as one of the largest continuous low-density structures ever measured in modern observational astronomy. The void occupies nearly 2% of the entire observable universe in volume. To cross it at the speed of light would take longer than the entire evolutionary timeline of complex life on Earth. Its sheer dimensions challenge standard astronomical models of cosmological structure formation. Surrounding this dark expanse are dense walls of galaxies, clustered together in long, interconnected threads. The stark contrast between these tightly packed cosmic filaments and the hollow interior of the void highlights a deep physical imbalance across the large-scale architecture of the cosmos. Understanding why such a massive gap exists requires examining how matter distributed itself shortly after the Big Bang. Tiny temperature fluctuations in the early plasma laid down the gravitational blueprint for every major galaxy cluster and empty pocket visible today across deep space. For decades, cosmologists assumed that cosmic matter was distributed relatively evenly across vast distances. The discovery of the Boötes Void shattered that assumption, forcing astronomers to rethink how gravity shapes the architecture of the universe over billions of years of cosmic time. During the mid-20th century, astronomers mapped the night sky using two-dimensional photographic plates. These detailed glass negatives captured the positions of celestial objects across the sky, but they lacked depth, obscuring the true three-dimensional structure of outer space. Without measuring how fast galaxies were receding, scientists could not calculate their true distance from Earth. A nearby dim galaxy and a distant giant galaxy appeared side by side on glass plates, creating the false illusion of a uniform, smoothly distributed cosmic fog. Edwin Hubble demonstrated in 1929 that the universe expands, causing light from distant galaxies to stretch into longer, redder wavelengths. Measuring this light redshift offered a precise mathematical key to unlocking the true third dimension of outer space. By the late 1970s, electronic spectrographs attached to ground-based telescopes allowed astronomers to systematically record galaxy redshifts. Researchers began assembling the first detailed three-dimensional maps of our local cosmic neighborhood, expecting to find mild variations in matter density. Early redshift maps compiled by Margaret Geller and John Hutterer revealed that galaxies were not scattered randomly like dust particles. Instead, they aligned along sharp filaments and broad sheets, leaving large empty pockets between them that hinted at an interconnected cosmic web. Cosmologists theorized that these discovered empty gaps were small localized fluctuations. Theoretical physics predicted that on scales larger than a few hundred million light-years, matter would smooth out entirely, appearing homogeneous and completely uniform in every direction measured. That theoretical model depended on the principle that gravity had not had enough time since the Big Bang to pull matter across vast cosmic distances. Discovering a gap larger than 300 million light-years across seemed physically impossible under existing models. In 1981, astronomers Robert Kirshner, August Oemler, Paul Schechter, and Stephen Shectman published a survey measuring galactic redshifts in targeted regions of the sky. Their initial goal was simply to record general galactic distribution patterns across deep space. The research team focused their survey on small, distinct field angles near the constellation Boötes. When they plotted the radial velocities of target galaxies along these sightlines, an unexpected gap appeared in their velocity distribution graphs across distinct target distances. Across a broad range of redshift values, corresponding to hundreds of millions of light-years in depth, galaxy counts plummeted to zero. Light from distant background objects passed through the area, but virtually no light originated from within the measured zone itself. Published in the Astrophysical Journal, the paper titled "A Million Cubic Megaparsec Void in Boötes" announced the detection of a colossal cosmic sphere devoid of matter. The astronomical community initially reacted with skepticism, suspecting observational errors or sampling defects. Skeptics argued that the original survey targeted narrow pencil beams of sky, potentially missing hidden galaxy corridors running directly through the region. To confirm whether the emptiness was real, astronomers needed to conduct broader follow-up observations covering a far wider field. Over the next decade, wider spectroscopic surveys confirmed the initial findings. The team expanded their search area and recorded hundreds of additional galaxy redshifts, yet the immense empty chasm remained stubbornly present in every single three-dimensional map they generated. The broader surveys confirmed that the void was roughly spherical, spanning nearly 330 million light-years across. It was bounded by massive galaxy superclusters, including the Hercules supercluster, which formed the rigid cosmic wall of the cavernous space. Popular science articles frequently describe the Boötes Void as completely empty, containing no matter whatsoever. This widespread claim is factually incorrect. Beginning in 1987, astronomer Greg Aldering and his colleagues began discovering isolated galaxies lurking deep inside the dark boundary. To date, astronomers have identified approximately 60 galaxies residing within the interior of the Boötes Void. While 60 sounds like a significant number, a typical region of this volume in an average part of the universe would normally contain over 10,000 galaxies. The galaxies found inside the void exhibit unusual physical characteristics. Most are unusually bright emission-line spiral galaxies that show signs of active star formation, arranged in a loose, tube-like alignment running through the center of the otherwise empty domain. Isolated from gravitational interaction with heavy neighbors, these interior galaxies evolved in extreme cosmic isolation. Without frequent galactic collisions or tidal stripping from dense cluster environments, they preserve ideal conditions for studying pristine star formation in low-density intergalactic gas. Computer simulations indicate that the few galaxies present inside the void were likely drawn along thin dark matter filaments. These delicate cosmic threads survived inside the low-density region while larger surrounding structures pulled the vast majority of available matter away. If observers lived inside one of these central void galaxies, their night sky would appear exceptionally dark. Before the development of powerful astronomical telescopes, sky observers on those worlds would see only total black space beyond the boundaries of their local star system. The verified existence of these 60 galaxies disproves wild claims of alien engineering or cosmic annihilation. Instead, it provides concrete empirical evidence that allows astrophysicists to test models of galaxy formation under conditions of extreme intergalactic vacuum. How did a void spanning 330 million light-years form within the current age of the universe? Standard models of cosmic evolution dictate that gravity alone could not have cleared out such an immense individual volume in 14 billion years. Cosmologists now understand that supervoids like Boötes do not originate as single, massive empty bubbles. Instead, they begin as several smaller, separate voids that grow independently, expanding outward into regions of slightly lower matter density during the early universe. Over billions of years, matter surrounding these smaller voids was steadily pulled outward toward denser regions by gravitational forces. As the boundary walls between neighboring voids thinned and dissolved, the empty pockets merged together to form one continuous giant cavern. The presence of dark energy significantly accelerated this void-clearing process over time. As dark energy causes cosmic space expansion to accelerate, regions with lower gravitational pull lose matter even faster, driving galaxy filaments outward into surrounding walls and superclusters. Modern sky mapping initiatives, such as the Sloan Digital Sky Survey, have uncovered numerous other giant voids across the cosmos. Discoveries like the Eridanus supervoid and Northern Local Void show that vast empty structures are fundamental components of the cosmic web. In the far future, as dark energy continues to stretch the fabric of space, voids will expand while galaxy filaments grow progressively thinner. Cosmic structures will grow increasingly isolated, separated by ever-widening expanses of empty darkness across an expanding universe. Looking out toward the constellation Boötes, telescopes record the cosmic web actively draining itself of matter. High above the desert horizon, optical mirrors capture faint ancient photons that escaped this deep abyss, leaving unresolved questions about where cosmic structure will ultimately drift.